You're probably aware that a dozen eggs is 12 eggs, and that there are 12 inches in a foot. These are examples of units of measure. In chemistry, the most important unit of measure is the mole, which is defined as the amount of substance that contains as many elementary entities as there are atoms in exactly 12 grams of isotopically pure carbon-12. The mole is important because it allows us to bridge the divide between the microscopic scale, which is composed of individual atoms, ions, and molecules, and the macroscopic scale, which contains enough material for us to be able to visually see, measure, and work with. In this photograph on the bottom, we see examples of 1 mole of a variety of different substances. And we can see that depending on the substance, even though they all have 1 mole, each substance occupies a different volume and a different mass. The number of entities in 1 mole is approximately 6.022 times 10 to the 23, which is of course the well-known Avogadro's number, which was named after the Italian scientist Amedeo Avogadro. The molar masses of the elements in the periodic table therefore allows us to calculate the molar masses of compounds. So, for example, in this case, where we asked to calculate the molar mass of sulfur dioxide, which has the chemical formula SO2, and here we have the Lewis structure for sulfur dioxide, we see that each molecule of sulfur dioxide contains 1 sulfur and 2 oxygens. And since sulfur has a molar mass of 32.07 grams per mole, and oxygen has a molar mass of 16 grams per mole, and we therefore have 2 of them in sulfur dioxide, we would therefore add these up, giving us a molar mass of 64.07 grams per mole for the molar mass of sulfur dioxide. This mole map allows us to do a number of conversions between the mass, the number of moles, and the number of chemical entities, whether those are molecules or atoms in a compound. So, for example, we can convert between the mass of a compound to the number of moles in that compound using the molar mass, or we could even convert between the mass of the compound to the number of moles of that compound to the number of moles of an element in the compound to the number of atoms of that element in the compound. So you see from this mole map, all that we need to know is the molar mass and Avogadro's number. And we can do a number of very important calculations. Zinc is a silvery metal that is used in plating iron to prevent the corrosion in a process known as galvanization. In this example, we are asked to calculate the mass of zinc given the number of moles of zinc. So the strategy we're going to use is we're given the number of moles of zinc, and we're going to use the molar mass, therefore, to calculate the mass of zinc. So again, we're going from the number of moles to mass using the molar mass. In this example, we're asked to calculate the mass of an element given the number of moles using the example for zinc. So here we see that zinc is a silvery metal that is used in plating iron to prevent corrosion in a process known as galvanization. And here we're asked to calculate the mass of zinc in 0.356 moles of the element. So in order to do this calculation, we're going to have to know the molar mass for zinc, which we can obtain from the periodic table. So looking up zinc in the periodic table, we can see it's located here, and this tells us that the molar mass for zinc is 65.38 grams per mole. So in this case, our strategy is to convert from moles to mass, and of course we're going to need the molar mass in order to do this. And we saw from the periodic table that the molar mass for zinc is 65.38 grams per mole. So there are a few ways to do this, but one of the easier ways is to use the ratio proportion method. So starting with the molar mass, which we know is 65.38 grams per mole, and we know that we have 0.356 moles of zinc, we want to solve for x, which would give us the mass of zinc in grams. Rearranging for x gives us 0.356 moles times 65.38 grams per mole. You'll see here that the units for moles cancel, leaving us with mass in grams, which is the correct unit for mass. Plugging this into your calculator gives us 23.27 grams. And since we have 3 sig figs in the starting number of moles, and our molar mass has 4 sig figs, our final answer should have 3 sig figs. You'll notice that I've kept one extra significant figure, which I've represented in lowercase. That would be for if we need to use this number in a further calculation later down the line. In this case, all we need is the mass, so we can round, which would give us 23.3 grams. The last step here is to check that our answer makes any sense. So you'll notice that the molar mass is 65.38 grams per mole, and we start with 0.356 moles, or a little more than a third of a mole. So our mass therefore should be a little more than a third of the molar mass. So in this case, the mass of 23.3 makes sense. In this example, we are asked to calculate the number of chemical entities in a given mass of an element. Here we're looking at sulfur, which is a non-metallic element that is present in coal. When the coal is burned, the sulfur is converted to sulfur dioxide, which is eventually converted to sulfuric acid, which gives rise to acid rain. Here we are asked to calculate the number of atoms in 16.3 grams of sulfur. So in order to calculate the number of atoms, we will first have to calculate the number of moles, which we will get from the mass of sulfur that we are given. So in order to do this, of course, we will need the molar mass of sulfur, and to convert from number of moles to atoms, we will need Avogadro's number. Looking at the periodic table, we see that sulfur, which is located here, has a molar mass of 32.06 grams per mole. As you may notice, we have two separate calculations to do. And although we can calculate these individually, it's generally faster to string these together while keeping track of the units using a process called dimensional analysis. So starting with 16.3 grams of sulfur, we know that we can convert it from mass to number of moles using the molar mass of sulfur, which we found was 32.06 grams per mole. In this case, because we want the grams to cancel, we're essentially dividing by the molar mass, which leaves us with the number of moles of sulfur. So now to convert from moles to atoms, we need Avogadro's number. And in this case, we'll have to multiply it by Avogadro's number, which is 6.022 times 10 to the 23 atoms per mole. And we can see here that in this case, the number of moles will cancel, leaving us with atoms of sulfur, which is exactly what we want. So plugging these numbers into your calculator should give us a value of 3.061 times 10 to the 23 atoms. You'll notice that the smallest number of significant figures here is 3, which is in the mass of sulfur. And so our final answer should have 3 significant figures. Therefore, rounding should give us 3.06 times 10 to the 23 atoms of sulfur as our final answer. In chemistry, we often have to move back and forth between the microscopic world, where we're dealing with individual atoms and molecules, and the macroscopic world, where we're dealing with grams and moles of material. The chemical formula of molecules tell us a lot of important information related to these microscopic and macroscopic worlds. So, for example, glucose, which has the chemical formula C6H12O6, tells us that in each molecule of glucose, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in each molecule. Similarly, we know that in each mole of glucose, there are 6 moles of carbon atoms, 12 moles of hydrogen atoms, and 6 moles of oxygen atoms. Now this information is important because it allows us to easily convert between the mass of a compound and the number of moles of the compound and the number of molecules of the compound. Similarly, we can go from the mass of the compound to the number of moles of the compound to the number of moles of an element in that compound, and then calculate the mass of the element in the compound or the number of atoms of an element in that compound. Okay? So using this calculation map, we can go from any one of these points to any other point along this diagram. In this example, we look at cisplatin, which has the chemical formula PtCl2NH3 2, which is used for the treatment of certain cancers. In part A, we are asked to calculate the number of moles in 285.3 grams of cisplatin. So in order to do this calculation, you'll see that in order to calculate the number of moles from the mass, we'll have to use the molar mass. Now in this question, the molar mass isn't given. However, we can calculate the molar mass from the chemical formula and the atomic weights in the periodic table. Cisplatin is composed of platinum, chlorine, nitrogen, and hydrogen. And using the molar masses for these elements, now we can calculate the molar mass of cisplatin from the chemical formula. You'll see here that we have one platinum, which has a molar mass of 195.1 grams per mole. We have two chlorines, which have a molar mass of 35.45 grams per mole. We have two nitrogens, which has a molar mass of 14.01 grams per mole. And we have 3 times 2, which gives us 6 hydrogens, which each have a molar mass of 101.008 grams per mole. So adding these up, we have a molar mass of 300.06 grams per mole for cisplatin. Now, in order to calculate the number of moles, one approach we can use is the ratio proportion method, and therefore starting with the molar mass of cisplatin, which as we said is 300.06 grams per mole, we can calculate the number of moles by placing on the other side the mass of cisplatin that we are given, which is 285.3. And therefore the number of moles will be given by the value x in the denominator. You can see here then that the grams cancel, leaving us with moles as our final answer, which is what we want. So plugging this into our calculator gives us 0.95096 moles of cisplatin. Now you'll see that the smallest number of sig figs in our quantities is 4 sig figs for the molar mass and 4 sig figs for the mass in our question. And so our final answer should have 4 sig figs. So our final answer is 0.9510 moles of cisplatin. The last part is to check our answer, and you'll notice that the molar mass of cisplatin is about 300 grams per mole, and the mass in our question is slightly less than 300 grams, and so we should have slightly less than 1 mole of cisplatin, which is indeed the answer that we have. So our answer should be correct. In part B, we were asked to calculate the number of atoms of hydrogen in 0.98 moles of cisplatin. Now, as we'll see, this is actually a multi-step calculation. In order to calculate the number of atoms of hydrogen, we will first need to calculate the number of moles of hydrogen, and in order to calculate that, we need the number of moles of cisplatin. The number of hydrogen atoms can be calculated from the number of moles of hydrogen using Avogadro's number. The number of moles of hydrogen can be calculated from the number of moles of cisplatin by simply using the ratio of the number of hydrogen atoms in each molecule of cisplatin. So in this case, we see that we have 6 moles of hydrogen in each mole of cisplatin. Now, since this is a multi-step calculation, the easiest way to do this is to string the calculations together, while keeping track of the units, of course. So, starting with the number of moles of cisplatin, which is 0.98 moles of cisplatin, we know that in order to calculate the number of moles of hydrogen, we know that we have 6 moles of hydrogen for each mole of cisplatin. So here we would multiply by 6 moles of hydrogen and divide by 1 mole of cisplatin. You can see here that the number of moles of cisplatin cancel, leaving us with a number of moles of hydrogen, which is what we want. For the next step, in order to calculate the number of atoms of hydrogen, we need Avogadro's number. And we know that in each mole, we have 6.022 times 10 to the 23 atoms per mole. And here we can see that the number of moles cancel, leaving us with atoms of hydrogen as our answer. So plugging these numbers into our calculator gives us 3.54 times 10 to the 24 atoms in 0.98 moles of cisplatin. Now we can see that 0.98 only has 2 significant figures, so our final answer should also only have two significant figures. So rounding, our final answer is 3.5 times 10 to the 24 atoms.